So the first thing we discussed is how to write the displacement time equation in SHM. The general equation would be like this: x is equal to a sine omega t plus phi. Phi is called the phase constant as you know it. And while deriving this, we even came upon this equation: v is equal to omega root a square minus x square. Using this equation, you can tell the speed of the oscillating object based on its position or displacement x from the mean position. Okay, then finally we discuss that time period, or we derive that time period is 2 pi divided by omega, that is 2 pi under root m by k. Omega is under root k by m. So when you send it to the numerator, it becomes under root m by k. Fine. Let's take one problem based on this. Suppose there's an object oscillating between the positions minus 20 centimeters and plus 20 centimeters. 0 being the mean position. And let's say initially the object is at the positive extreme. So at t is equal to 0, the object was here and it was released from here. Now there's a restoring force acting on it, so it will start oscillating. Amplitude is given, and assume the mass of the object is 2 kg, and the force, the restoring force acting on it is given by F is equal to minus, say, okay, let's say minus 10 x, where x is the displacement from mean position. So force is given, mass is given, amplitude is given. Now you can write everything about this. I mean, you can find out everything about this particle. So first thing I want you to do is derive omega, then write the position or displacement time function, not position time, displacement time. Then you know from where it is released. So based on that, derive its speed when the particle is at the mean position. Okay, try all these. I'll give you 3 minutes. Right, I got one answer for omega as root 5, then position time, displacement time equation as 0.2 sine root 5t plus pi by 2, and third one as 0.2 root 5. Okay, let's see. See, the force is minus 10x. We know omega in simple harmonic motion, we call it as angular frequency, okay, is given by under root k by m, where k is the force constant, the proportionality constant between force and displacement, and m is the mass of the oscillating object. Substitute that here, it becomes under root. The force constant is 10, mass of the object is 2 kg, so this becomes root 5. And the unit for omega will be second inverse. Okay, dimensionally also you can derive. Next, the displacement time equation. See, it's very easy to write the displacement time equation. Here the particle is oscillating with equal amplitude on both sides. Usually that is what happens unless you disturb it in between. The general equation is given by this formula: x is equal to a sine omega t plus phi. Okay, we had derived this in general, where a is called amplitude of oscillation. Now, what is amplitude? Amplitude is the maximum distance the particle oscillates away from its mean position. Now, it was released from plus 20 centimeters. No, they're released from rest. So there the speed is 0. So it is understood that this is an extreme position. Okay. So distance from mean position to extreme position, this itself is what you call as amplitude, which in this case is 20 centimeters, that is 0.2 meters. So we got amplitude, we already got omega. Next thing we need is the phase constant. Okay. See, this entire bracket is called the phase of oscillation, and only this term is called the phase constant. You can call phi, that is the phase constant, as initial phase also. Why? Because omega t plus phi is the phase. When you substitute t as 0, then the phase will be phi itself, no? So phi can also be called as initial phase. That means phase value at t is equal to 0. So initial phase or phase constant mean the same thing. Now what are the factors on which that depends? Phase constant depends on where the particle is at a particular time. Usually initial position will be given to you. So where it is at initial time, it is based on that. And which way it is moving also, it depends on that. Now see, we are writing the position or displacement time equation in terms of the sine function. When writing in terms of the sine function, we already know the phase constants. For negative extreme, it is 3 pi by 2. For mean position going forward, it is 0. For positive extreme, it is pi by 2. For mean position going backward, the phase constant will be taken as pi. Okay. Now, where was this particle released from? It was released from the positive extreme. So the phase constant you take is plus pi by 2. So we know that as well. Therefore, the displacement time equation becomes amplitude 0.2 sine omega is root 5 into t plus phase constant is pi by 2. Next, what is the speed of the particle when it is at mean position? When you gave the answer is correct only. Which equation did you use? Or which formula did you use? To get the speed when the particle is at mean position, which formula did you apply?
Sir, omega into root a square minus x square.
Okay, we know speed as a function of position of the object. V is equal to omega root a square minus x square. When it is at mean position, x, that is displacement from mean position, is 0. So this becomes omega root a square, which is simply omega into a, or a omega. Fine. Amplitude here is 0.2 meters. Omega is root 5. So this becomes 0.2 root 5 meters per second. And we had discussed this at the beginning itself, beginning of this chapter, that when a particle oscillates back and forth in simple harmonic motion, it will be moving the fastest when it is at the mean position. Okay, so you can also say this is the maximum speed of the particle during oscillation. They can ask you a question like that also. What is the maximum speed it attains? So you need to remember that speed will be maximum at the mean position. While going towards the extremes, it slows down. When it is at the mean position, it will be moving the fastest. Okay, fine. The general displacement time equation for simple harmonic motion on a straight line is like this. X is equal to a sine omega t plus phi. Now, if you know the displacement time equation, differentiating it will give you the velocity time equation. So if you differentiate this, you get velocity as a function of time as a. The derivative of sine function becomes cos omega t plus phi, but you are differentiating with respect to time. T has a coefficient omega, so this whole thing gets multiplied with omega. So the velocity equation or the function can be written as a omega cos omega t plus phi. Okay. So if this is the displacement time equation, then this is the velocity time equation. Okay. Both are oscillating functions. Try to we'll visualize what that means. Now x is equal to a sine omega t plus phi. We know that the sine function takes a maximum value of plus 1 and a minimum value of minus 1. So this part's maximum is plus 1, minimum is minus 1. So it oscillates between minus 1 and plus 1. Now if that part, sine part, oscillates between minus 1 and plus 1, then a multiplied with the sine function, then this whole function should be oscillating between minus a and plus a. And we know that. Okay, this equation represents the motion of a particle oscillating between minus a and plus a. This is how the function represents that. Now do the same analysis with the velocity equation. The velocity equation is written in terms of cos function. Now cos also, as time keeps varying, the phase will keep changing. That means the term inside the cos bracket will keep changing. Then it will keep oscillating between minus 1 and plus 1. Those are the extreme values of the cos function. But when it comes to velocity, that cos function is multiplied with a omega. Therefore, this whole function, if you see, the whole velocity function, if you see, its minimum value will be minus a omega and its maximum value will be plus a omega. So those are the two values between between which velocity oscillates. Okay. So the highest negative velocity that the oscillating particle can have is minus a omega, and the highest positive velocity it can have is plus a omega. Fine. Similarly, acceleration. You differentiate the velocity function, you will get acceleration. Otherwise, you can use the condition for SHM also. We know acceleration is minus omega square multiplied with x in simple harmonic motion. So you can simply write it as minus omega square. X function is a sine omega t plus phi. Okay, even if you differentiate the velocity function, you will get the same result. But I am using a is equal to minus omega square x. Now you observe this part, this equation. Again here, the sine part oscillates between minus 1 and plus 1. as time varies. But now the sine function is multiplied with minus a omega square. So the extreme values of this will be minus a omega square and plus a omega square. These are the maximum accelerations that the oscillating object can have. Notice that the acceleration of the object executing simple harmonic motion is also an oscillating function. Okay, we had discussed this at the beginning of this chapter when we basically analyzed qualitatively analyzed oscillations. We discussed that acceleration will be variable, and now we see mathematically that it will be varying as a sinusoidal function or an oscillating function, you can say. Okay, now restoring force is proportional to displacement from mean position. Let us discuss it here itself. Suppose there's an object oscillating on this straight line. Between minus a and plus a. Okay, this kind of visualization is important while solving problems. 0 is the mean position. Okay. So imagine an object oscillating between x is equal to minus a and x is equal to plus a. See, the displacement is obvious. Wherever you put the particle on this line, that is where the object is. Now, if you think in terms of velocity, we know that at the ends, that means at the extremes, the velocities are zeros. So here v is 0, here also v is 0. And we just derived that the maximum velocity that the particle can have is plus a omega, minimum is minus a omega. And we know that when it crosses the mean position, it will be moving the fastest. So when it is moving or passing through the mean position in the positive direction, its velocity will be plus a omega. When it is passing through the mean position in the negative direction, its velocity will be minus a omega. That is what it means. Next, acceleration. Now, acceleration depends on force. And we know that in simple harmonic motion, restoring force depends on the displacement from mean position. Greater the displacement from mean position, stronger the restoring force. So when the displacement from mean position is maximum, that means when the particle is at positive or negative extremes, the restoring force will be strongest. Therefore, the acceleration also will be strongest. Now, we just derived that maximum positive acceleration is plus a omega square. And negative acceleration maximum is minus a omega square. So when will it have those? See, when the particle is at the positive extreme, we know the force will be negative. Force will be to the left. Okay. Therefore, here the acceleration will be negative maximum, that is minus a omega square. When particle is at the negative extreme, force is positive, means acceleration will be positive and it will be the strongest. So here the acceleration will be plus a omega square. Fine. That is how acceleration varies as the particle oscillates back and forth. At mean position, the net force is 0, the restoring force is 0. Therefore, acceleration also will be 0 at mean position. Till then, it would have accelerated, but at that moment, it will not accelerate. Okay. Next, when the displacement time equation is x is equal to a sine omega t plus phi, differentiating this, we get the velocity time equation as a omega cos omega t plus phi. Now, cos function can be expressed in terms of the sine function, right? So you can write it as a omega sine, see, cos alpha is sine alpha plus pi by 2. You can always do this. So cos omega t plus phi can be written as sine omega t plus phi plus pi by 2. Usually, like, see, you also have cos alpha is equal to sine pi by 2 minus alpha. Usually we don't do it like this because in place of alpha in simple harmonic motion equations, we'll have this phase, which is omega t plus phi. If you write minus alpha like this, then it becomes minus omega t plus phi. We try to avoid that. We write omega t as the first term with a positive coefficient. Okay. There is mathematically nothing wrong in doing this also. If you want to convert cos to sine, or sine to cos, you can simply use the fact that cos alpha is sine 90 minus alpha, that is pi by 2 minus alpha. You can do that, but usually we don't write equations with a negative coefficient for time. We try to keep the coefficient of time positive. Okay. Now you observe the displacement equation and the velocity equation. When we write both of them in terms of the sine function, okay, the peak value is obviously different. Peak value of displacement is A. Peak means maximum. And the peak value of velocity is A omega. Of course, they are dimensionally different quantities altogether, so their peak values will also be different. Okay. Look at the phase now. The phase of the displacement function is omega t plus phi. Okay, phi depends on where the particle was at initial instant and which way it was moving. We know how to write phi. Okay. And look at the phase of the velocity function when written in terms of the sine function. It is omega t plus phi plus pi by 2. When both quantities, displacement and velocity, are expressed in terms of the same function, sine function, look at their phase values. One has a phase of omega t plus phi, the other has a phase of omega t plus phi plus pi by 2. So the velocity function has a phase of pi by 2 more than the displacement function. So we say that velocity leads displacement by a phase difference of pi by 2. Okay, there is a difference between the phase of the displacement function and the velocity function. The difference is pi by 2, and which is having more phase? Velocity function is having a greater phase because it's omega t plus phi plus pi by 2. Velocity function is having a greater phase compared to the displacement function. So since it has a greater phase, we say velocity leads displacement by a phase difference of pi by 2. You can also write it in reverse. You can say displacement lags velocity by a phase difference of pi by 2. Same thing. The meaning is the same. Okay. Now, why do we care about what is the phase difference between them? Who is leading, who is lagging? You'll understand. Okay. What this means is, see, when this term becomes 0, let's say at some time this has become 0, then here also it will be 0. But the whole phase of the velocity function, if you see, when omega t plus phi is 0, this becomes pi by 2. Now, when angle is 0, sine value is 0. But when angle is pi by 2, sine value is maximum. That is the significance here. When angle is 0, that means when displacement is 0, the velocity becomes maximum. Okay, that is what we mean by having a phase difference of pi by 2, or one function being pi by 2 ahead in phase compared to the other function. When one is at mean value, the other will be at extreme value. Means when the particle is at mean position, velocity of the particle will be having its extreme value. That means maximum velocity. Now, you can look at it this way also. When this bracket, when omega t plus phi becomes pi by 2, then this bracket becomes pi. Okay. When angle is pi by 2, sine function becomes maximum plus 1. Okay. So when displacement from mean position is maximum, again, when angle is pi, sine function becomes 0. When displacement is maximum, velocity comes down to 0. 0 is not the minimum, 0 is the mean value. Negative is the minimum. Okay. Negative extreme is the minimum. So what this means is when displacement of the particle is maximum, displacement of the particle maximum means what? It is at positive extreme plus a. There the velocity becomes 0. That is what we mean by having a phase difference of pi by 2. Both are sine functions only. They have a phase difference pi by 2. Now, in an interval of pi by 2, what happens is the sine function goes from extreme value to mean value, or mean value to extreme value. One of those things will happen in an interval of pi by 2. So that is what a phase difference of pi by 2 signifies. When one is at mean value, like displacement is 0, velocity will be at its maximum value. Or it could be at minimum value also. It depends which way it is moving, positive direction or negative direction. Next, when one is at extreme value, let's say displacement is extreme, like positive extreme. then velocity will be 0 there. When displacement is negative extreme also, velocity will be 0. That is what we mean by a phase difference of pi by 2. And remember this also. How did we do all this analysis? We first expressed both quantities, both displacement and velocity were expressed in terms of the same function, the sine function. Then only you can compare the phase values. You can't write one in terms of sine and one in terms of cos and say they have the same phase. No, sine function and cos function are not the same. Okay, so you should make the function same first, then see the phase difference between the two quantities. Okay, so between displacement and velocity in simple harmonic motion, there is a phase difference of pi by 2. Velocity will be leading by a phase difference of pi by 2. Okay, next acceleration. Acceleration as a function of time, we know it is minus omega square multiplied with x. And we have written the equation also here. Minus omega square multiplied with x becomes minus a omega square sine omega t plus phi. Okay. So acceleration function, if you see, minus a omega square sine of omega t plus phi. Now acceleration is already written in terms of the sine function. But if you see the coefficient is negative, we should remove that. You should make it positive. Now you all must be aware that sine alpha is negative of sine alpha plus pi. You add an angle of 180 degrees. Okay. Sine function remains the sine function itself. But if you add angle 180 degrees, the angle goes into the third quadrant where sine is negative. So sine alpha is minus sine alpha plus pi. Or you can write it in reverse. Minus sine alpha can be taken as sine of alpha plus pi. You can even take it alpha minus pi, doesn't matter. Okay. So acceleration function written in terms of the sine function becomes a omega square sine omega t plus phi plus an angle of 180 degrees, that is pi radians. This is the phase of the acceleration function. Okay. Now compare the phases of displacement and acceleration. Displacement, the phase value is omega t plus phi. Acceleration phase value is omega t plus phi plus pi, 180 degrees. Therefore, acceleration and displacement have phase difference of pi between them. Now you cannot say which one leads and which one lags. Here I have written plus pi, so it looks like acceleration phase is more than displacement phase. But instead of plus pi, you could have written minus pi also. The function would have remained the same. So when it comes to acceleration and displacement, you will not say which one is leading, which one is lagging. Okay, it doesn't make sense to say anything like that. They have a phase difference of pi. Now what does a phase difference of pi signify? Pi is exactly half the period of the sine function. Okay. So in a duration of pi or when angle changes by pi, half the sine function will be complete. What does it mean by half the sine function completing? Let us look at the graph for sine function that we had drawn in the last class. Yeah. Consider 0 and pi. Now what is happening at 0? At 0, the sine, when angle is 0, the sine function is also 0, but it is about to increase. It is about to become positive. When angle is pi, the sine function is 0, but it is about to become negative after that. Okay, that is what we mean by a phase difference of pi. Exact opposite things will be happening. Mean position increasing, the opposite thing is mean position decreasing. What does that mean? What does it signify for the relation between displacement and acceleration? Let us discuss that also. Now, they have a phase difference of pi. Now, when displacement is 0, acceleration also will be 0. And that makes sense. Displacement 0 means mean position. At mean position, acceleration is also 0. But see, suppose the particle is at mean position going in the forward direction. Means next instant, displacement will be positive. But when it is going in the positive direction, acceleration will be negative. So displacement acceleration come to 0 at the same time, same position, but at the next instant, when one is positive, the other will be negative. They do the exact opposite things. Okay. Now consider some other interval. Interval of pi itself, but starting point and ending point will change. Let's consider these 2 points. an angle pi by 2 and an angle 3 pi by 2. Pi by 2, 3 pi by 2 also have a gap of pi between them. But you see how these two are opposite. When angle is pi by 2, the sine function takes a positive extreme, plus 1. Or when it is multiplied with amplitude, it becomes plus a. When angle is 3 pi by 2, the sine function takes the negative extreme value, minus 1. Exact opposite. So that is what we mean by having a phase difference of pi in a sine function. Exact opposite things will be happening with the quantities. Now, how do we relate this to displacement and acceleration? Now, when the particle is at positive extreme, displacement is plus a. But look at acceleration. Acceleration is minus a omega square. So displacement, when displacement is positive maximum, acceleration is negative maximum. That is what we mean by having a phase difference of pi. They do the exact opposite things. Both will reach extreme positions, but when one is at positive extreme, the other is at negative extreme. When one is at negative extreme, the other will be at positive extreme. They'll be oscillating in the exact opposite manner. That is what we mean by having a phase difference of pi. Okay, so having phase difference pi by 2 means 1/4 of the sine function, sine cycle. So when one is at 0, the other will be at extreme. When one is at extreme, the other will be at 0. Having a phase difference of pi means half of the sine function. Okay, so when one is at negative extreme, the other will be at positive extreme. When one is at mean position going down, the other will be at mean position going up. Okay, they'll be doing the exact opposite things. So displacement and velocity have a phase difference of pi by 2, velocity leading the displacement by pi by 2. Displacement and acceleration have a phase difference of pi. They do the exact opposite things, or they behave in the exact opposite manner to each other, you can say. Okay. Uh, See, based on a given situation, you understood how to write the equation, displacement time equation. Let us do the reverse now. Try to solve this problem. Let's say the displacement of an object is given as a function of time by this equation, 0.5. Okay. All quantities, all terms are in SI units. X is equal to 0.5 sine, say, okay, pi t plus pi by 2. And the mass of this object is given as, say, 4 kg. So a 4 kg object is oscillating according to this equation. Find out, first thing, what is the time period of oscillation? Next, what is the maximum speed during oscillation? Next, write the equation for restoring force. Okay, solve these three parts first. I'll give you 2 minutes. This is quite easy. Right. Now, in the displacement time equation, the 0.5 is amplitude, pi is omega, and pi by 2 is the phase constant. That's all. Basic formula for time period is 2 pi by omega. Omega is pi here, 2 pi by pi. The time period becomes 2 seconds. That means it takes 2 seconds to complete one oscillation. Okay. What is the maximum speed during oscillation? We have a formula for maximum speed, a omega. If you don't remember it, just differentiate the displacement equation. Then you will get the velocity equation. From that, you can tell what is the maximum. Okay. So maximum speed during oscillation is given by a omega. A is 0.5 here and omega is pi. So you can say maximum speed is pi by 2 meters per second. Okay. Then the restoring force. Restoring force, there are many ways to express it. It's basically minus k into x. Okay. But we don't know k value here. We know omega. Omega is under root m by k. Omega square, sorry, omega is under root k by m. Or directly, omega square is k by m. In the derivation, this is the substitution that we used. So k can be written as m omega square. So you can write the restoring force as minus m omega square x as well. So if you want to write it as an equation, as a function of displacement, it becomes minus. The mass here is 4 kg. Omega square, omega is pi, then it becomes pi square multiplied with x. And pi square, you need to remember this, pi square is approximately equal to 10. So sometimes in options they keep it as pi square. Sometimes they replace it with 10. Then if you take pi square as 10, then this changes to minus 40x. They can give you this also in the options. So you should remember that pi square is very close to 10. Okay, that is the restoring force. Now, depending on the position, you can tell how much is the force. Vanilla, you gave one definite answer for restoring force. You said it is minus 4 pi square x. Okay, 4 pi square, then you changed it to 4 pi square x. Okay, fine, fine. Now, based on the given equation, you all tell me, where is this particle initially? Initially means at t equal to 0, what is the position of this particle? Can you repeat?
0.5, sir.
X is equal to 0.5. It is at the positive extreme. You can tell that simply based on the phase constant. The phase constant here is plus pi by 2. Now, for which initial position do you have a phase constant of plus pi by 2 for the sine function? Positive extreme. Or you substitute t as 0, then what does this function change into? X is equal to 0.5 sine pi by 2. Sine pi by 2 is 1. 0.5 into 1 is 0.5. So it is at the positive extreme at t equal to 0. So not just at t equal to 0, you can tell its position at any time. By differentiating this, you get the velocity equation, and then you can tell its velocity also at any time. You can tell acceleration also at any time. Okay, that is why this equation is very important. You can describe almost everything that you need about the particle that is oscillating. Okay. Next, suppose you are asked something like this. A particle is oscillating between x is equal to minus a and plus a. Okay, let us do a qualitative analysis first. Let's say it is oscillating between minus a and plus a. You know how speed varies during oscillation, right? At extreme positions, the speeds are 0. But as it comes to mean position, the speed increases. And again, as it goes closer to the extreme, the speed decreases. Fine. Let this be the mean position, x is equal to 0. Now, let us consider some more positions. Let's say x is equal to plus a by 2 and minus a by 2. Okay, the negative side will come to a little later. The entire oscillation takes a time equal to the time period, 2 pi by omega. Suppose you release it from the negative extreme. To go from here to the positive extreme and come back, it takes a time of 2 pi by omega. That is what we mean by one oscillation. Suppose you release it from the negative extreme, starts oscillating, goes to, sorry, you release it from the positive extreme, goes to negative extreme and comes back. This also takes the same time, that is time period. Suppose it was already oscillating and you started observing it when it is at mean position going forward. Then mean position going forward to positive extreme, coming back to mean position, going to negative extreme, and then coming back again to mean position. This is what we mean by one complete oscillation. And this will take a time of one time period. Irrespective of where you start observing it from, if one oscillation is done, the time taken will be time period itself. Okay. Now you imagine the particle moving from, or imagine it oscillating. Let's consider one part of the oscillation when the particle is moving from mean position to the extreme position. Now when it moves from mean position to extreme position, it will have to cover this displacement first and then the remaining displacement, a by 2 to a. Okay. The displacements are equal. Here it's a displacement of a by 2 or it is moving by a by 2. The next part also it is moving by a by 2. But let's say the time taken for this part of the journey is t1 and the time taken for this part is t2. Now you all, both of you, think carefully and give me an answer. Which time will be greater? Will it take equal times to cover these intervals or these distances, or which time will be greater? Okay, give your answer in chat. I'll give you 1 minute. Okay. See, you are given two certain displacements, 0 to a by 2 and a by 2 to a. Which displacement takes longer is the question. Now, if the distances being covered are same, okay, don't think about SHM generally. Suppose a person A is covering some distance and another person B is also covering the same distance. If you have to decide who covered the distance faster and who took longer to cover the distance, what information do you need to know? What other information do you need to know? Two objects are undergoing the same displacement. You need to decide which object undergoes or which object takes more time to undergo that displacement. Amount of displacement is same. So what other information do you need to decide who took longer?
Their velocity, sir.
Their average velocity, okay, or average speed, you can say. Now, Vanilla, you only tell me, as the particle is oscillating, the two displacements that we have considered are first one is from mean position to half of the amplitude, and the second displacement is half of the amplitude to complete amplitude. The green part and the yellow part. In which part will the object be moving faster in general? Or will it move with same average speeds?
In the first part, sir.
In the green part, it will be moving faster. We know how the velocity varies during oscillation. At mean position, it is the fastest. As it goes closer to the extreme, the velocity decreases. And at extreme position, it becomes zero. So, the first part of the journey will be covered faster. Second part will be covered slower. But the distances are same. Then obviously, the first part will take lesser time. Okay, second part will take longer time. We will find out the exact time also for this. We have the displacement time equation. The displacement time equation is very useful. X is equal to a sine omega t plus phi. This is the displacement time equation. Now, if you want to represent this particular motion using this equation, this particular motion starts from mean position. Okay, and it is going in the positive direction. When particle is at mean position going in the positive direction, the phase constant will be taken 0. So the function becomes x is equal to a sine omega t. Okay, understand how to use this equation to find out time taken for a certain displacement. Now, according to this equation, when t is 0, displacement will also be 0. Makes sense. Okay, now what do we want to know? We want to know the time it takes to reach a by 2. Then what will you do? You'll just substitute the displacement as a by 2, that's all. Observe carefully. Based on the initial position and direction of motion, we determined that the phase constant is 0, and this is the equation, displacement time equation. We want to know the time it takes to reach a by 2. Then just substitute x as a by 2 in the equation. If you substitute x as a by 2, cancelling a on both sides, what will you be left with? You will be left with 1 by 2 is equal to sine omega t. Okay. Now, you all tell me, sine of what angle is 1 by 2? Eh, Sine of what angle is 1 by 2? Okay. Pi by 6 radians, 30 degrees, pi by 6 radians. So, one of the solutions of this equation is omega t is equal to pi by 6. But that's not the only angle where sine function becomes 1 by 2. There are many other angles as well. You can have angle as 30 degrees, 180 minus 30, that is 150 degrees is possible. Then again, 360 plus 30, 390 degrees is possible. 360 plus 180 minus 30. 360 plus 180 is 540 minus 30 is 510 degrees. Infinite solutions will be there. Any trigonometric equation has infinite solutions. You know that. We want to know the first time it gets to a by 2. No? We took time here as 0. We assumed it's at the mean position when time is 0. Then what is the first positive time when it reaches plus a by 2 is what we want to know. Okay. For that, like in trigonometry, I think you learn this primary solutions, or what do they call it? A solution for a trigonometric equation which falls in the range minus pi to plus pi, I think. Okay, anyway, let's not get into mathematics. That name is not important. So you take omega t as pi by 6. That's the first possible solution, first positive solution for this equation. Then you get t is equal to pi by 6 omega. Okay. Now, how much is time period? Time period of oscillation is 2 pi divided by omega. So, pi by omega can be written as time period divided by 2. If you do that, pi by omega is written as time period by 2, then this becomes time period by 6 into 2, that is 12. So, the time taken to go from 0 to a by 2, the time taken for the first part of this journey is 1/12 of the time period. When expressed in terms of time period, it is 1/12 of the time period. Okay. So let me quickly revise or remind you how I solved this. At t equal to 0, it's at x is equal to 0. We want the time it takes to reach a by 2. So I put the position or displacement as a by 2 in the equation and got the time from there. Okay. Now one of you tell me, how will you find out this time, the time taken for the second part of the journey? How can that be derived?
Find out the total time taken from X to A.
Okay. Find out the time taken to go all the way from 0 to a. And from that you subtract the first part, time taken for the first part, you'll get the time for the remaining part. Okay. Do this both of you. You know the equation x is equal to a sine omega t. This is the equation which represents this particular oscillation starting from mean position at t equal to 0 going forward. We want to find out the time it takes to reach the positive extreme. Okay. At positive extreme, you know x is equal to plus a. So substitute that and find out a value of time. Express it in terms of the time period. It is time period divided by how much. Do that and then subtract the first time from this. You'll get the time taken for the second part of the journey. Do this both of you. I'll give you 2 minutes. Okay, good. Both of you gave the same answer. Time period divided by 6 and that is correct. Now when you substitute x as plus a, you get a is equal to a sine omega t. Cancel the a's. You get sine omega t is equal to 1. When does that happen? When the angle omega t is pi by 2. So t becomes pi by 2 omega. And when expressed in terms of time period, this will be time period divided by 4. 1/4 of the time period is what it takes to go from mean position to extreme position. Remember this also. This part of the oscillation takes exactly 1/4 of the time period. Now, in this part of the oscillation, from mean position to one of the extremes, in this case, the positive extreme, all possible velocities will be touched. Sorry, all possible speeds will be touched. At mean position, it moves the fastest. At extreme position, the speed becomes 0. And in between, it will cover all the values. It will touch all the values. So that takes a time of t naught by 4. The reverse journey will also take the same amount of time, t naught by 4. Because there also it will be touching all those velocities over the same displacement. Next, to go from mean position to negative extreme also, it will take the same amount of time because it will be touching all the speeds from maximum speed a omega to speed at the extreme position 0. It will touch all the speeds. So it takes the same time t naught by 4. And to come back from negative extreme to the mean position also, it will take the same time t naught by 4. So 4 times of t naught by 4, that gives the time period t naught. So if you take intervals where all velocities are touched, then in those for those intervals, the time taken will be the same. But you look at this part of the journey, 0 to a by 2 and a by 2 to a. 0 to a by 2, all velocities will not be touched. A by 2 to a, all velocities, all speeds will not be achieved by the particle. Okay, all possible speeds won't be achieved. And 0 to a by 2, the average speed it attains is more. A by 2 to a, the average speed it attains is less. Now T1 we found out as T naught by 12 and T2 when expressed in terms of time period turns out to be T naught by 6, which is basically longer. Okay, so random intervals if you take, Even if the displacements are equal, there's no guarantee that the time taken will be equal. It depends on the velocities that are being, or the speeds that are being attained during that displacement. We'll work more on this. There is a concept called uniform circular motion, or simple harmonic motion as a projection of uniform circular motion. If you understand that properly, then you will be able to tell the time taken for any part of the journey very quickly. There are easier ways to do this. Okay. We'll discuss all that. But keep this in mind. When it is near the mean position, it will be moving fastest. When it is near the extremes, it will be moving slower. Okay. Fine. So you know how to write the equation depending on omega value and where it is starting from. You know how to find out the time taken for some part of the journey at least. Okay.
Sir, in the velocity of sir, the time taken by the object to move from 0 to a by 2 is it equal to the time taken by the object to move from a by 2 to 0, sir?
The first part of your question, your voice was breaking. Can you repeat when the velocity? Or
Time taken by the object to move from mean position to a by 2, is it equal to the time taken by the object to move it from a by
okay,
2 to mean position?
okay. Time taken to go from 0 to a by 2 and a by 2 to 0. You tell me. Uh, let's call this as forward journey and backward journey. Is it taking the same speeds during the forward journey and backward? Is it like whatever speeds it is attaining during the forward journey, will it attain the same speeds at the same positions during the backward journey also or not?
Yes, sir.
It will. Okay. Because V is equal to omega root a square minus x square. For a given x value, you will have two possible V values. For example, suppose x is equal to a by 4, 1/4 of the amplitude. When you substitute it here, V becomes omega root a square minus x square, that is a square by 16. You do that, it will become under root 15 by 16, that is omega root 15 divided by 4, but you have to take plus or minus. Okay. So when it is at a particular position like a by 4, it can have two possible velocities. Forward motion omega root 15 divided by 4. Backward motion omega minus omega root 15 divided by 4. But the speed is same, no? So at a particular position, it takes the same speed. So to cover the forward journey and to cover the backward journey, it will take the same amount of time if the journeys are the same. Yes. So T naught by 12 and a by 2 to 0 also it takes the same time T naught by 12. How to mathematically prove that it takes T naught by 12? Uh, that you'll understand. When you learn how to represent SHM as a projection of uniform circular motion, it'll be very easy for you to find out the time taken to complete any part of the journey. Not only starting from mean position, starting from anywhere to anywhere, you can easily tell how much time it takes. Okay. Any other questions? Fine, let's solve some more problems also. One more question we'll take. Based on the same equation, x is equal to a sine omega t. Actually, in questions, they won't give you this equation mostly. They will describe a certain part of the journey. Like the last question we solved, I asked you to compare or find out the time taken to go from 0 to a by 2 and a by 2 to a. So it is obvious that the particle should be starting from 0. Starting means not starting from rest. When you look at it first, or when t equal to 0, the particle is at x is equal to 0 going forward. When t equal to 0, particle is at mean position going forward. Based on that, I wrote the equation and then solved the problem. This you are expected to do. Depending on the situation that they describe, you should be able to write its position time or displacement time equation. Okay. Now, I won't give you the equation. You decide how the equation is going to be. The only thing you have to decide is the phase constant. Rest of the equation is standard only. I want you to find out average speed of the particle. Okay. What is the formula for basic formula for average speed? Total distance by total time. Find out the average speed of the particle when it moves from negative extreme to positive extreme once. Do this quickly. And I want answer in terms of amplitude and time period. In terms of that, I want the answer. Okay. Think carefully and solve both of you. Okay, I got one answer as 4a by t naught. That is correct only. Now imagine the object going from minus a to plus a. We want the average speed, which is total distance divided by total time. And you were asked in terms of time period. When it goes from minus a to plus a, the distance covered is 2 times the amplitude. And the time taken, we have already discussed that from 0 to a, it touches all possible speeds. So this is exactly one fourth of the cycle, one fourth of the oscillation. Then this part also will be one fourth of the oscillation, T naught by 4. T naught by 4, T naught by 4. So going from negative extreme to positive extreme, half oscillation is done. Time period will be half of the time. Sorry, time taken will be half of the time period. And divide them, you will get the average speed. That will become 4a divided by T naught. Okay, you don't even have to use the equation, displacement time equation to solve this problem. Just imagine it oscillating on a straight line. From where to where do we know the time taken? Based on that, you can tell the average speed. Okay. You can even calculate average velocity. Average velocity is total displacement divided by total time. Now, when it goes from minus a to plus a, in that part of the oscillation, it's not changing direction. And if it's not changing direction, then we had discussed this in kinematics itself. If the direction of motion of an object does not change, then average speed and average velocity will have the same magnitude. So average velocity for this part of the journey is also 4a by t naught itself. And direction, it's in the positive direction. So you can write I cap or plus 4a by t naught and so on. Okay. So tomorrow's class will discuss further about this equation, time taken to travel some part of the journey, cover some part of the journey. And tomorrow we'll also discuss some systems which undergo linear oscillations and how to find out their time period, how to write position time equation for that particular system. Mostly we'll be dealing with spring block systems. We'll talk about some other cases of oscillation as well. Okay. Thank you all. We'll continue in tomorrow's class. And please join on time. Vanilla joined today. Very good. Aishwarya, you also join on time from tomorrow's class.